I'm going to do some of the practice problems that I assigned because I thought some of you might like to see the examples done out rather than just the answer in the back of the book. So number 41, we see the integral has a sum in the numerator, a sum in the denominator. Usually, if you have a sum in the denominator like this, you want to let that be u. Try it first, and you're hoping for 1 over u du. So if u is equal to x squared plus 1, du is 2x dx. And there's no way that we can turn x plus 4 dx into 2x by multiplying by a constant. So what I can do is I can split this integral into the integral of 1 over x squared plus 1 times x dx plus 4 times the integral of 1 over x squared plus 1 dx. So this is arctan here. That one is exactly fits our formula. And here this is 1 over u, and we need just a 2. So I can supply the 2 here and a 1/2 on the outside. And what I have here is 1/2, I'll go ahead and write it, 1/2 the integral of 1 over u du. And that will be, integrating, we'll have 1/2 times the natural log of the absolute value of u, but u is positive, so I don't need to write the absolute value signs. Natural log x squared plus 2 plus 4 arc tan x plus a constant. Problem 45, again, we see that we have we have an inside function here, something under the cube root that is a sum, a quadratic. So I would hope that I could turn this into u to the 1/3 in the denominator. So I'm going to let u be the inside function, 3x squared plus 6x plus 5. Then du is 6x plus 6 dx. And that looks really good because on the top we have x plus 1 dx. So notice du is 6 times the quantity x plus 1 dx. And I'm going to be able to get what I want up here by just multiplying by 6 and 1/6. And you see yourself how that turns into 1/6 times the integral of, and here's the du. I have x plus 1 here, x plus 1 times 6 dx. That's my du. So this is simply u to the 1/3 in the denominator, so it becomes, in moving it up, u to the minus 1/3 du. And we integrate 1/6, raise it by 3/3, so we get 2/3, multiply by its reciprocal 3/2. So let's see, we get 1/4 u, which is 3x squared plus 6x plus 5 to the 2/3 plus a constant. Number 49, again, I see a sum that's being squared, and I'd like to turn that into one term. I'd like to turn it into just a u squared in the denominator. That would become u to the minus 2. So I let u be x plus 1, and du is dx. So, well, I'm not going to be able to multiply by a constant to turn that numerator into dx. So what I do in this case is I'm going to change the entire integral into a u integral. And so I need to solve for x, and then I'm going to put it in right here. So x is equal to u minus 1 using this. And I get, changing this all into terms of u, 2 times u minus 1, the quantity, plus 3 over u squared du. dx is du. Multiplying it out, we have 2u plus 1 over u squared du, which is the integral of, and I would just split this and get 2u over u squared is 2 over u plus 1 over u squared du. And so I would write that using, let's write it one other way. It's 2 times the integral of 1 over u du plus the integral of u to the minus 2 du. Now integrating, we have 2 times the natural log of the absolute value of u, which is x plus 1, plus this will be u to the minus 1. So that is x plus 1 to the minus 1 times the reciprocal of minus 1 plus a constant. You could simplify that slightly. Number 65, again, I always try to choose u to be the inside function. I'd like that to be u to the 1/2. I see right away that my du is going to be just have one factor of x, and I have 3 of them here, so there's going to be a problem. But let's just see if we can turn it all into terms of u and make it a u integral. So u equals x squared plus 2, du is equal to 2x dx, and changing this, writing this, not changing it yet to a u integral, I'm going to write it as the square root of x squared plus 2. I know that that's the same thing as u to the 1/2. And I have an x dx I could use, but I have an extra factor of x squared, don't I? X squared times x is the x cubed. And all I need is a factor of 2 here to turn this into du. So I need a 1/2 out here, and I have an extra factor of x squared. In other words, if I tried to change this to u right now, I would have u to the 1/2, and I'd have du, but I have that x squared. Well, fortunately, we can solve for x squared here. X squared is equal to u minus 2. So what I put in here is u minus 2. Multiplying it out so I can use the power rule, I'll have u to the 3/2 minus 2u to the 1/2 du. Integrating, we have 1/2, and I'll raise, let's see, I'll put that in brackets now so I don't forget to multiply across with the 1/2. I'll have u to the 5/2 times 2/5 minus 2 times u to the 3/2 times 2/3. And now I want to multiply across, and then I'll put it in terms of x. So 1/2 times 2/5, I have 1/5 u to the 5/2 minus, let's see, the 1/2 and the 2 cancel, so I have minus 2/3 u to the 3/2, and put it back in terms of x. So I'll go back in white. Go back in terms of x, and we have 1/5 times the quantity x squared plus 2 to the 5/2 minus 2/3 times the quantity x squared plus 2 to the 3/2 plus a constant. Now the remaining 2 or 3 problems are to show you how to do definite integrals, which was discussed in the lecture that I posted. We're going to change the integral into a u integral and change the x limits to u limits. So again, we see we want to pick the inside function for u and write u equals 1 plus x squared. So du is equal to 2x dx. And that looks good. If I give myself a 2 here and a 1/2 on the outside, I have 1 over u cubed du. So I'll write this as 1/2 the integral of u to the minus 3 du. Now the problem is that these limits are from x equals 0 to x equals 2, and we've done a transformation here. We've changed the integral into a function of u, the integrand. So we have to change the limits also. So let's see, I'll pick a different color because this is the point of this. If x is equal to 0, then u is equal to 1 plus 0 squared, 1. And the upper limit, x equals 2, is transformed into u equals 2 squared plus 1 is 5. So the limits of integration here are 1 to 5, not 0 to 2. So you just continue to integrate and finish in terms of u. You never go back to x. You don't need to. This is a signed area. And if you look at that video that I posted for you, you can see that we're just transforming the x region into a different region in a different plane. If this is the xy function, we might say we're transforming it into a uv plane. And we have a different region, but the area, the signed area, is the same. So we just integrate, adding 1, u to the minus 2 times minus 1/2. And we're going to evaluate between 5 and 1. So we have negative 1/4, and I'll just evaluate the 1 over u squared, 1 over 25 minus 1 over 1, and simplify that number, and that is the signed area. In problem 71, again, we're going to pick the inside function and let it be u equals natural log x. Du then would be 1 over x dx, and this just fits perfectly. This might take you an extra step to get here, but it's the sine of u times 1 over x dx du. So this is going to be minus the cosine of u, but we're not going to evaluate it between e and 1. We have to change our limits of integration. So if x is equal to 1, then u is equal to the natural log of 1, which is 0. And if x is equal to e, then u is the natural log of e, which is 1. So our new limits of integration are from 0 to 1. So we'll just write minus the cosine of u, and we're going to evaluate it between the limits 1 and 0. So we have minus the cosine of 1 minus the cosine of 0, which is minus, I don't know what the cosine of 1 is. The cosine of 0 is 1. So our signed area under this graph, function of x, or if we had a uv plane, it would be the area under the sine of u from 0 to 1. And let's see, that is 1 minus the cosine of 1, a number. Well, you can see right away that this is a simple integral. It's just simply the integral of u cubed du. If u is equal to sine x, du is cosine x dx. So that's u cubed du. But again, we have to change the limits of integration. If x is equal to 0, then u is equal to the sine of 0, which is 0. If x is equal to pi, then u is equal to the sine of pi, also equal to 0. So this is rather easy to evaluate, isn't it? There's no signed area under the graph of u cubed between 0 and 0. Our answer is simply 0. Now that must make you wonder a little bit about this graph. It must have equal areas above and below. And so I quickly checked it on Mathematica, and it looks just like this. I think. Oh boy. I think it looked like that. Just a sec, I'm going to check. Well, it looked just about like that. It looks more like this, but it doesn't make any difference. It looked more like that. But anyway, same thing. The plus and the minus, the positive and negative contributions are the same in magnitude. So the signed area is 0. So I hope this helps you understand more the lecture that was posted and be able to do these problems on the quiz tomorrow.